Yeah, so it's most recent match queries and online suffix trees, and I suppose you know what suffix trees are, but I'm going to give you my angle of them anyway. So this is a suffix tree that indexes this string down here, and the way the strings are contained in the tree are by labels on the edges. So, for instance, the string DA, which we have somewhere here, is located on the end of this edge, coinciding with this node here. And up here we have a point that coincides with, well, it doesn't coincide with a node, but it's still a point that represents the string YA. So it's not just the nodes that represent strings, it's also the points between the characters on the edge labels. And every leaf, every endpoint of every external edge corresponds to a suffix of the string, but not all. So in many contexts, it's common to require that the final character of the string is unique, which makes it a one-to-one correspondence, where each suffix is also a leaf. But in this case, we're not requiring that. So, for instance, the suffix consisting of the single character A is on the edge, at the edge end of this edge label, coinciding with this node. And the next suffix is at this point. I'll get to why this is marked this point later. And then when we get to the next longer suffix, this is indeed located on a leaf, and then after that all the longer suffixes will be on leaves, because once you found a suffix that's contained only as a suffix and not elsewhere in the string, it's a leaf. And since it contains all suffixes, it also contains all prefixes of suffixes, which is all substrings. So for instance, we have the string ADADA. We find that by going from the root ADADA, stopping at that point. And we can find any pattern that's present in the string. We can find any string here in time proportional to the length of the pattern. So we just walk down from the root and find the pattern in the tree, requiring that we can do the choice between characters at nodes here in constant time, which we can do if we have a constant size alphabet or if we use hashing. So we assume that. Now, we want linear size of the data structure, which means we can't store every edge label separately. So instead, every edge label is stored as a pair of pointers into some position in the index string where that label string is. So in this case, we can have this label represented as pointing to this substring or to this substring. It doesn't matter. In some cases, it does matter. For instance, here, you may think that this label could be represented as either of these three, but in fact, it cannot, because, well, it can only be this one. And that's because we don't only use the pointers from the labels to the string as finding the labels. We also use them as for finding the position in the string of the pattern. So in this case, we want to find the pattern DYA corresponding to this point. And then we have to use this one, because this is not DYA, this is AYA, and this is not DYA either. In some cases, it doesn't matter. So here, this edge label D could be either one of these three, because AD is here, and it's AD everywhere here. So usually, we won't care here. A normal suffix tree, we won't care which of these three the edge label points to. However, what's special in this talk is that we do care, because we want to find the most recent match. So it would be nice if we could have this always point to the rightmost position of the rightmost candidate, which is not what we usually get. If we use Ukkonen's algorithm, which we're going to do, we are going to point to one of the first two, usually the second one. We could also make it point to the first one, but making it point to the last one is much more difficult. Yeah. So Ukkonen's algorithm is online, meaning that we can get from this situation where we have a suffix tree of a number of characters from 0 to I-1, and then include one more character, which we haven't looked at before, in constant time, transform this tree into this tree that has one more character in it. Also, in some situations, we want to do the reverse. We have a tree that incorporates the whole string, and we want to remove the last character, making it the suffix tree containing only this part of the string. And Fiala and Green showed how to do that in an amortized constant time. And if you combine that with Ukkonen's algorithm, you get a proper sliding window index, which is what I did in this paper in '96, which it puts it in a compression context. And after I did that, I published the code on the web, and a lot of people used it. And a number of people have then emailed me over the years and asked me, does your data structure find the most recent copy of the string? And if it doesn't, how do I do that? And I've always had to say, I don't know, and it doesn't. So that's why I wanted to tackle this problem. And why would you want to do that? Well, probably they're using it for Lempel sieve compression, which means you want to find, it's nice if you find the most recent one, because that makes it easier for the next phase of the compression. It makes it easier to entropy code the position of the string more efficiently, using a Huffman code, for instance. And other people have tried that previously, so here's some previous results. There's one paper by Amir Landau and Ukkonen that does this with a logarithmic additional factor, except that it doesn't solve the general problem. It only it finds the most recent match of suffixes of the currently indexed string. So you can only match at the end of what you're currently looking at with the window. And I'm not sure it even solves the sliding window problem anyway. Fragina, Nito, and Venturini solved the problem without the log factor. But not only is this not online, it's also, well, it's not only is this specialized for sieve Lempel, so you can only find the sieve Lempel factorization. You can only find the most recent match for the sieve Lempel factor, so it's not general patterns, and it's not online, so it would be impossible to use for a sliding window. This work by Kroshmore, Languin, and Mignosi do work with a sliding window. It's online, but they cheat a little bit. They don't actually give the most recent match. They only give a recent match that's recent enough in order to be coded in the fewest number of bits, given some premises for the entropy coding. So this work supports general most recent match queries for arbitrary patterns, and we do it with a logarithmic factor. And I'm going to move back to Ukkonen's algorithm. So the reason why I marked this point is because that's the active point at this point of when we've indexed this string, which means that it corresponds to the longest suffix that also appears somewhere else. And Ukkonen's algorithm works by keeping track of the active point. That's the deepest point in the tree where we may have to do some structural change in the next iteration. So if we do the next iteration, we add one more character. Let's say the next character is y. We're going to start working here. And the reason why we don't have to work on deeper points is because these edge labels, the edge labels of external edges leading to leaves, don't have an endpoint. These labels are always on the end of the string, so we keep the endpoint implicit. And when we add something to the string, it just automatically adds it to all the leaf labels. We don't have to do anything for that to happen, because the endpoint of those labels are just pointing to whatever is the end of the string right now. So the first point we have to deal with is the active point. And in this case, we have to put in a y here. If this would have been a y, we would have just walked down there. But in this case, we have to put in a new leaf with a y there. And then we have to move up to the next point in the tree where we may have to do something. And then we use the other trick, which comes from McRae's suffix tree construction algorithm, the suffix link. So we follow this. We get, using a backwards pointer in the tree called a suffix link, we get from this point to this point where we get from the point that represents YA and remove the first character, so we get to the point where we represent A. And that's the next position where we may have to do something. In this case, we don't have to do something because there is a Y here already. So we just move down here and get that as the new active point for the next iteration. Okay, so here's the suffix link in another tree. This node added above the root is an idea from Ukkonen, which makes this node the target of the final suffix links. Now, these suffix links are not quite as McRae's and Ukkonen's. These are my version of them. They are not between nodes. They are between edges. That has some efficiency considerations, which I'm going to present at another conference. But it also makes it easier for the description here, because we're going to convert the edges of the suffix tree into nodes in another tree. It works the same way. It's just that so for instance here, if we look at the string represented by, we have, for instance here, we have ABDA. Following the suffix link here, we can get to the point representing ABDA minus the first A, which is BDA, so we get to this point. And from that, we get to the point for DA by following this link here. And then we get to the point for A here. That's the point for A. And then from, no, sorry. Yes, it is. OK. And then we get to the point for, yeah, it gets a bit tricky at the end here because of the edge links. But the final point is always this one, this edge that represents the empty string. So then we're going to look at another tree, like this. Oh, sorry. Let's move to that first. So here's the tree that consists not of these nodes. In this tree, we've taken every edge of the suffix tree and made it into a node. And the suffix links are the edges. So the root of this tree is this edge here that goes between up tack to the root. We call that right tack. This is going to make it more convenient in the following algorithm. So let's move back to the most recent match problem. So what we do in one iteration of Ukkonen's algorithm is we start at an active point, and we do some work here, possibly do some work here and here and here, until we find a position where the character we're adding is already present, and then we just move down and stop. So this is the normal path that we traverse during one iteration. So it's fine if we do updates on this part. However, if we want to keep the most recent match for every pattern, we should update everything on the whole path up to here. So we should continue along this path. We can't do that because that gives us superlinear time. We can, however, traverse this path when we're matching a string, because if we've matched a string of length p, a string p with a pattern p gone down here, for instance, then we've already spent the time proportional to the length of the string, and we can afford to move back up in the same time. So we can just add the same amount of time for going back up. And that's what we're going to use to just put the most recent match. We're going to see that the most recent match pointer is somewhere all along this path. So when we match, we go down, and then we move back up following the suffix links. And somewhere on that path, we find the most recent match. So I'm going to have to do this quickly because I'm running out of time. Oh, that's not good. Oh, right. So what we're going to preserve then is this property. We update the position of an edge when when the active point reaches the end of that edge. And then for the link tree nodes, every link tree node in this tree, we maintain a representative that points to a descendant, the descendant of that node that has been updated most recently. So for that's not quite true. So the property is for every node, there is an ancestor in the link tree that points to the most recently updated in this subtree. So for instance, let's say we're at node 8, we want to find the most recent match. Then we know that the most recent match is going to be somewhere along this path. And to range that, when we update, so that's what we do here, maintaining the property. When we update something, the position of something, we set the root node's representative to the most recent match. So in this case, if we update this one, we're going to set the position of the representative of the root to this one. So then we've fixed the problem for this whole path. Problem, of course, is that then we overwrite something, so we might have destroyed the property for this path. So therefore, we have to we take the old value and the new value, take the lowest common ancestor of those, which is this one, and then we push the old value down from here to just below the lowest common ancestor. So that fixes it in this case. In general, we may have to push recursively further down the tree, so we may have to push all the way down the link tree to the end. So that looks like it could be a lot of updates. Fortunately, it's possible to construct a tree that's completely balanced, which would not be updated more than the link tree. So we can guarantee that the number of updates is only n log n. So that's not so bad. We have one more problem, which means that we have to use another data structure. We use something from Breslau and Italiano, which keeps track of the current implicit suffixes in the tree. And we use that to find the position when we're matching a pattern at an edge that has not yet been position updated because the active point hasn't moved past it yet. So then we've covered all the cases. OK. And we want to be able to use this as a sliding window, for a sliding window too, and we can do that. Just use the normal Fiala and Green technique, and all the other data structures can be dismantled from behind, so we can use it for a sliding window. This is a bit more interesting. We can actually, in the case where we use this for what we would usually use it for, the Ziv-Lempel factorization, we don't have to pause update every time. We can wait until we get to the end of the current factor. And then we can do the updates for that whole factor backwards. And that saves us some updates because we can avoid updating the same value twice or several times in the same iteration. And actually, I don't know what the time complexity is then. It destroys the worst case that I've found for the original algorithm, but haven't been able to deduce the exact time complexity. Okay, so we've showed that you can do this for arbitrary strings in an online suffix tree with logarithmic factor, which is nice, but I do consider this, if you compare this to what I set out to do, it's actually a bit of a failure because I wanted to do it in linear time, and also I would like to have a practical data structure for actually doing this. Here we use dynamic lowest common ancestor stuff and things that are pretty difficult to implement, and I'm not sure that somebody would actually use this in practice for this problem. So there's still some interesting things to do here to find a practical data structure, lower the log n bound, or prove maybe an upper bound. It's not clear if this can be done in linear time or not. Okay, thank you.
Any question? Simon.
So I'm not quite sure I understood this correctly, but so with the LZ case, does that mean you're spending log n time per factor?
No, I actually don't know how much time I spend per factor there.
Okay.
If I update for every character that's included in the suffix tree, then there is a worst case. I've found a worst case. There is an adversary example that makes it n log n. Okay. In the case where you take a whole factor at a time and update backwards, I haven't found an adversary case, so I don't know what that is.
Thanks.
Another question? Gregory. Back.
I just also missed. So this works only when you append, you maintain to appending a letter to the right, right? So does it work for the sliding wheel? Or that it
Yes, it does. I just mentioned that briefly. Yes, you can just use the normal techniques for dismantling the tree from behind. It's nothing new there, but it does work.